Hello, Math 1050. This is a video for section 3.4 on polynomial functions as their graphs. So the past couple of sections, we've been working with polynomials. We've been learning how to divide them. We've been learning about how to find their zeros, but we haven't really looked at their graphs. What do the graphs look like when you take some inputs and find some outputs and put them on a coordinate plane? To get an idea of what they might look like, let's graph some basic ones. So if you take a look at this top left one, we've seen this one before. All the outputs equal just the inputs. That's a straight line. We know that as the identity function. And then if you go down instead of across, if you go down to x squared, we know that as a parabola. We've seen that a lot. And I think we've even seen a couple times the cube function. So that's in the middle column, first row here. However, we haven't explored a whole lot powers greater than 3. If we look at power that is 4, x to the fourth, look at that one and notice how similar it looks to the parabola. And if we look at the power of 5, notice how similar that looks to a power of 3. And power of 6, very similar to the power of 4 and 2. And now maybe you see why I have them in rows this way, where I've got the odd powers on the first row and the even powers on the second row, because those ones are the ones that are similar to each other. And if we look at these, what would the end behavior be? For example, if you look at the odd powers, when the x values go to the right, what are the y values doing? And you may notice that the y values are heading straight up on all of those ones on the first row, all of the ones with an odd power. If you go to the left, what are the y values doing? They aren't going straight up, but they are going down to negative infinity. So they all have the same kind of end behavior there. And if we look at the even powers in the second row, their end behavior, whether you go to the right or to the left, the y values are going up in each instance. So we can make some predictions with that then. If we look at this table down below, fill in the table with the end behavior. If we have a positive leading coefficient and an even degree, so that would be the second row here, then our end behavior would look something like this. Now, there might be some other things that are happening in the middle near the origin, but as you go off to the sides, that's what the end behavior would look like. And if it's an odd degree, like the first row, then the end behavior is not quite like that, but as you go to the left, it goes down, and as you go to the right, it goes up. Now, if you recall what happens when we multiply functions by negative values, when we multiply the outputs, it kind of flips them, right? So if I were to say negative x squared, we would have a parabola that's facing down. If I were to say negative x to the fourth, we would have the x to the fourth function going down. So if we have a negative leading coefficient, then our end behavior on even degrees would be going to negative infinity in both directions. And the negative coefficient would flip the odd degrees such that it goes to positive infinity when you go to the left and negative infinity when you go to the right. So those are some features of polynomials. When you graph them, the end behavior can be found using that following that chart there with the even degrees and odd degrees by identifying the leading coefficient and the degree of the polynomial itself. Now recall that we've been finding zeros as well. Zeros are the x-axis of the graph of a polynomial function, because if the y value is 0, then whatever x value makes that y value 0, that's where you would cross the x-axis here. And this is important. If we read this statement here, it says, there are as many complex zeros as the degree of the function. If you remember the word complex, it doesn't necessarily mean something's difficult here in the mathematical context. It's talking about complex numbers, a real number plus an imaginary number, a plus bi. So when you add up the real numbers, or the real zeros and the non-real zeros, there are as many as the degree of the function. So if you take a look at this first one, it is degree 2. We can see that because it's a parabola. And it crosses, well, before we look at how it crosses, since it's degree 2, from that statement up there, we know that the total zeros are 2. Like both real and non-real, all of them, there's 2 because it's a second degree. And if you look at the x-intercepts, it crosses the x-axis twice, and those correspond with real zeros. So we have 2 real zeros. Now, if we have a total of 2 zeros, and 2 of them are real, then that's all of them, so therefore there are 0 non-real zeros. And the leading coefficient, if you look at the end behavior here, since it's an even degree and the end behavior is going to negative infinity on both sides, the leading coefficient would have to be negative. If we look at the 5th degree, total zeros would be 5. That's the same as the degree. And if you look at the real zeros, it crosses the x-axis in 3 different spots. So that would correspond with 3 different real zeros. And that means that that's not all of the zeros, so there must be 2 left over since we know there's a total of 5. So 2 of them must be non-real. They're not showing up on the graph because the graph has a real axis for the x-axis and a real axis for the y-axis. So the non-real zeros are not going to show up on the graph. If you look at the end behavior, it would help us find that the leading coefficient would be positive. It matches the end behavior of a positive odd degree. If we look at the 4th degree, total zeros would be 4, but it does not cross the x-axis at all. So none of those zeros would be real. Therefore, there are 4 non-real zeros. And the leading coefficient, since it's even degree and end behavior is both going up, it would be positive right there. Positive leading coefficient. For the 3rd degree, that would be 3 total zeros. We see it crosses the x-axis once, so that would be 1 real zero. That means there have to be 2 non-real. And the leading coefficient on this one, it's kind of upside down from the other odd degrees that we had, so it would have to be a negative leading coefficient. Okay, so when a polynomial function is expressed as an equation, there's 2 main forms that we like to deal with. We've got standard form and factored form. You guys are familiar with standard form and factored form right there. Both of them are good in different ways. There's pros and cons to both. So here is a graph of the polynomial that is shown in standard form and factored form. So these are the exact same polynomials, just written in different forms, and this is the graph of that polynomial. So if you look at the end behavior there, it's easiest to identify the end behavior using standard form because we can easily see the degree and the leading coefficient. So standard form is the one to use for identifying end behavior. And for identifying the y-intercept, if you look at the y-intercept on the graph, it's -6. And if you look at standard form, there's a -6 right there. That's not just coincidence. If you were to type in 0 for x, all of those would go away except -6. So we would have a point at 0, -6, which is the y-intercept. So standard form is good for finding the y-intercept. So factored form must be good for something, and it is good for identifying zeros. If you take a look at the graph, we've got x-intercepts at -5, -2, and +3. that can be found by setting f of x equal to 0, and then setting that factor equal to 0, that factor equal to 0, and that factor equal to 0, and getting the x-intercepts. So for identifying zeros, factored form is the one that we like. Let's go ahead and take a look at example 1. It says, I graph the function by identifying the zeros and behavior and one other point. So if you look at this, it is in factored form. So it's going to be really easy to identify our zeros. Take that, set it equal to 0, take that factor, set it equal to 0, and take x plus 1 and set it equal to 0. So our zeros would be 0, positive 3, and negative 1, and those correspond to x-intercepts. So I can put a point at 0, 0, and negative 1, 0, and 3, 0. Now the end behavior, standard form is good for that. So you might think we'd have to multiply this out. However, we don't have to multiply the whole thing to find out what the leading term would be. The leading term would come from multiplying 2x by x, and then that results by x. So I guess it'd look better if it's 2x by x, and then that multiplied by x. So the leading term would be 2x cubed. So since it's 2x cubed, positive and a positive leading coefficient and odd degree, that means our end behavior would be looking something like that. So we'd have something going up like here, and the end behavior of that one going down like that. And finally, on MyMathLab, it asks for one other point in order to help determine what happens in between everything. So you can just pick an x value and find what the y value is. I like picking easy ones, so I picked 0, or excuse me, I picked 1. You can't pick 0 because we know that the output is at 0 because we have a x-intercept there. So I picked 1, and that would be 2 times 1 times 1 minus 3 times 1 plus 1. And we get a result of negative 8. So there's a point at 1 and negative 8, and when you do that, you can fill in the rest. Oh, that does not look very nice. But MyMathLab makes it look really nice. And we've got a polynomial looking something like that. Maybe I could make it look a little better. It's okay. Let's take a look at example 2. Graph the function by identifying the zeros, end behavior, and one other point. So similar to the last one, however, this one is now in standard form. So that means we can identify the end behavior really easily. We see that the leading term is x cubed. So that means that our end behavior is going to be looking like that. Positive leading coefficient, odd degree. And then we got to find the zeros. Well, standard form is not very nice for zeros. Factored form is, so let's factor it. We've got 4 terms here, so let's use factor by grouping. There's a greatest common factor of x squared in the first 2 terms. And then I'm going to say that negative 1 is the greatest common factor of the second 2 terms. And then you notice that I have x minus 7 and x minus 7. I can treat that like a greatest common factor. Okay, x minus 7 times x squared minus 1. And then this can go further. X squared is quadratic, so I want to see if I can get it all the way to linear terms. And I've got, that's a difference of squares right there. So x squared minus 1 would factor to x minus 1 times x plus 1. So therefore, our zeros are at 7, positive 1, and negative 1. So let's go ahead and see what this is starting to look like. Negative 1, positive 7. And then we know our end behavior is looking like this. So we need one other point. I can plug in 0 for this one because I haven't yet identified what the output is at 0. So that'll be nice. That will make lots of things go away. We'll have 0 cubed minus 7 times 0 squared minus 0 plus 7 gives us an output of 7. So at 0, 7, I can plot that point and then try my best to make this look like something. Looks a little better than the last one, maybe. And that would be a sketch of the key features of that polynomial function. Another thing to be aware of are repeated zeros. So zeros that come up more than once. If a 0 is repeated, and if it comes up an even number of times, when it's repeated, we say it has multiplicity. So if the multiplicity is 2, 4, 6, 8, so on and so forth, if it's an even number, then that does something kind of different where it crosses the x-axis. It doesn't just cross straight through it. It actually causes what we call a tangent point. So if you look at the examples here, it just kind of hits the x-axis and then it turns back around in the direction that it was coming from. So that's with even multiplicity on zeros. Odd multiplicity will cross through the x-axis. It will cross through. If it's multiplicity 1, it just like straight through, doesn't do anything weird. But as soon as it hits multiplicity of 3, 5, or 7, then you might be familiar with this with the cube root or the cube function. It kind of comes in and flattens out and then goes back up again. We call that a terrace point. A terrace point. So again, that happens on odd multiplicities bigger than 1. So let's take a look at example 3. It says sketch the graph of the function. That is in it's in factored form. So finding the zeros should be really easy. Our zeros would be 3, but notice how it's x minus 3 raised to a power of 2. So that means that there's x minus 3 twice. There's 2 factors that are x minus 3. So that means that it's got multiplicity, and the multiplicity is 2. And then the other 0 would just be negative 5. It doesn't have any powers on it, so it doesn't have any multiplicity. So if we think about this, at positive 3, we've got a tangent point, so it's just going to bounce off the x-axis. At negative 5, it doesn't do anything weird, it's just going to go straight through it. Now let's think about the end behavior. End behavior is going to come from multiplying it out to standard form, but we don't have to multiply the entire thing out. Just think of what would happen if we did. We would have x getting squared and then multiplied by another x. That would be x cubed, and then we have a negative out front. So the leading term, if we were to multiply it into standard form, would be negative x to the power of 3. So therefore, our end behavior is going in opposite directions, and it's been flipped. So we've got end behavior going up like this, and then we can come down here, make it go like that, and then notice how I created a tangent point at positive 3 because it had even multiplicity. If we take a look at practice A, that is also in factored form, our zeros would be at negative 1 and positive 4 would have a multiplicity of 3 because of the power of 3 on it. So I can put a point on the x-axis at negative 1 and at positive 4. If we were to get this into standard form to identify our end behavior, we would have x being multiplied by x cubed, so that would be x to the 4th, and it would be positive. We don't have a negative out front. So this would be an x to the fourth polynomial. So we know that our end behavior would be going up like this on both ends. And then it's going to cause a terrace point at 4 because of the multiplicity. So make it kind of flatten out there. And then it will go just straight through -1. It's not going to be a terrace point. It'll just cross straight through it. Okay, example 4 is going backwards. It's saying use the graph to find the factored form of the function. So if we take a look at that, it is in standard form, and maybe we could factor that if we wanted to. However, it says use the graph to do it. So if we look at the graph, I notice that it has x-intercepts, or in other words, zeros, at -5. If you count over, that hits at -5, and it's a tangent point at -5. So that's got to be an even multiplicity. Let's just say multiplicity 2, unless we realize we need it to be bigger. And then it crosses right through the origin, so it's got a 0 at 0. And then it comes back up and it crosses through at 8. So those are all the zeros. Now let's turn those into factors. Let's turn them into factors. So we can say that f of x will be equal to x plus 5 is the factor that would give -5 as a 0. And it's got a power of 2 because we see that it's a tangent point. And then 0, the factor that gives 0 is just x. And then the factor that gives positive 8 would be x minus 8. And that's as far as we need to go on that one. That would be factored form of that function. So they also ask us in this section to use transformations to graph polynomial functions. So remember that if you add a number to the input before it goes into the function, that is a horizontal shift. If you add a number after it's come out, so you add it to the output, that's a vertical shift. And then these things right here, the things that are being multiplied out front, those are going to stretch it. Oops, sorry, it jumped back up to the top. Let's get back there. So we were talking about vertical stretch on the outside. So let's go ahead and take a look at example 5. So it says use transformations to sketch the graph of that function right there. And if you look at it, it is a cubic function because of that power of 3 there. So normally that would look something like this. But now it's been transformed. So the plus 5 moves it to the left 5. And the plus 4 will move it up 4. So the middle point, which is called the inflection point, is now at -5 and 4. And then the negative out front will flip it upside down. It reflects it. So let's flip that upside down. And we might have a cubic function that looks something like that. So the blue one is what we're looking for there. On practice B, notice that the power is a power of 2. We know that's quadratic, so the shape would be a parabola. And it's been moved to the right 2 and up 3. So let's move it to the right 2 and up 3 for the vertex. And then the 1/5 is a vertical stretch by a factor of 1/5. So this one's kind of interesting. What happens is, to identify our growth pattern, it actually goes up 5 over 5. So I'm going to go up 1, 2, 3, 4, 5, and over 1, 2, 3, 4, 5. And it'll do that on the left as well. It'll go up 5 and over 1, 2, 3, 4, 5. And the reason for that is because if this were not transformed, like if this were at the origin, then if an x value of 5 would give you a y value of 25, right? Because 5 squared is 25. But then it gets multiplied by 1/5, which cuts it by 1/5, and so instead of going up 25, it would only go up 5. So right 5 and up 5. I'll do that again for the left side. So again, if this had not been shifted, and if it were at the origin, and it had 1/5 out in front, then an x value of -5 would give a y value of positive 25, right? -5 squared is positive 25. But then that gets multiplied by 1/5. And 1/5 of 25 is 5. So the y value isn't 25, the y value is 5. And that'll happen anytime you have a fraction like that as a vertical stretch in front of a parabola. So if it's 1/3, then it would go up 3 over 3. If it's 1/4, it'll go up 4 over 4. This one was 1/5, so it's up 5 over 5, and we can sketch our parabola through there, and left 5, up 5. Looks like I forgot to do the increase and decrease of the functions, both of them. Let's go ahead and take a look at that. So example 5, where is the function increasing? If we're looking at the blue one, it's always going down when we read it from left to right. As we read it from left to right, it is always heading down. So therefore, it does not have any intervals of increase, so not applicable. And it is increasing on its entire domain, which is -infinity to infinity. If we look at the parabola on practice B, it's increasing at this part, and that is at an x value of 2, so 2 to infinity. And it's decreasing from -infinity all the way to that x value of 2, so it's decreasing from -infinity to 2. Okay, let's keep going. Next, we've got the intermediate value theorem. The intermediate value theorem says that if you have two outputs where one is above the x-axis and one is below the x-axis, then you know there has to be a place in between there that crosses the x-axis. Okay? For example, I'm just going to do a blank coordinate plane here. If you found an output that is below the x-axis, and then later on you found an output that is above the x-axis, if you're dealing with polynomials, you know that somewhere in between there, it's going to cross the x-axis. That's called the intermediate value theorem. So let's see what they're asking us to use that for. Example 6 says, use the intermediate value theorem to show that the polynomial function has a real zero between the numbers given. So we're not asked to find the zero, we're just asked to prove that it has one in between the numbers given. So here's the polynomial, and it wants us to show that it has a zero, or it crosses the x-axis, between 1 and 2. In order to do that, let's find what the outputs are at 1 and 2. Okay, so let's plug in 1. If we do that, we get -6. Let's plug in 2. If we do that, we get +4. So if we look over at the graph, I have 1 and -6, and 2 and +4. Notice how one of those outputs is below the x-axis and the other output is above the x-axis. That means that there has to be a place in between there where the polynomial crosses the x-axis there. So we can say, since f of 1, which is 6, is below the x-axis, and f of 2, which is 4, is above the x-axis, there must be a 0 in between. We know there has to be a 0 between 1 and 2. So that's the intermediate value theorem. Okay, we're almost there. Let's take a look at example 7. Example 7 says, find a polynomial of least possible degree having the graph shown. So if I look at the graph, I see that it has some points for us. The first points that I'm looking at are the x-intercepts, and those correspond with the zeros of the polynomial. So we would have zeros at -6, +4, and +9. Let's turn those into factors. The factors that are associated with those zeros are x plus 6, x minus 4, and x minus 9. So now I've got a polynomial that I can make with those factors of x plus 6 times x minus 4 times x minus 9. That would have those exact same x-intercepts. But would that have the exact same y-intercept of 108? It might not. In fact, if we multiply it out, if we get it into standard form, we've got 6 times -4 times -9. That would come out to be 216, which is not 108. So that does not have the correct y-intercept. So how do we get the correct y-intercept? Well, we say that it's been stretched. There's a vertical stretch happening. We're going to call it A. And what we're going to do is we're going to multiply out our polynomial to get it into standard form. So let's multiply the last two. We're going to multiply x to x and -9 and -4 to x and -9. So we'll have a times x plus 6 times x squared minus 13x plus 36. And then let's keep going and multiply through the x plus 6. Got to make sure we keep track of all of our terms. But eventually we would get x cubed minus 7x squared minus 42x plus 216. So, as I mentioned, that would have a y-intercept of 216, but we want a y-intercept of 108. So what would we have to do? What stretch do we need in order to get it to 108? Well, 108 is half of 216. 108 is half of 216. So that means that A has got to be 1/2 that would bring down the y-intercept from 216 to 108. So if a is 1/2, then the last thing we'll want to do is distribute the 1/2 through to get it into real standard form. We don't have parentheses when we are in standard form. So our result will have that, our final result will have that 1/2 distributed through. And it gives us that function right there. So that function has the correct x-intercepts because we started with those factors. And then we changed the vertical stretch so that it would pass right through 0 and 108 because that 108 is half of 216, which is what the y-intercept would have been without the stretch. Okay, let's try practice C. Similar idea. Let's go ahead and identify our zeros. So we've got zeros at -1 and 2. However, notice something. This is usually catches some people. Do you notice something about the x-intercept at -1? It is a tangent point. So it's got to have even multiplicity. Now, because it says polynomial of least possible degree, we're going to make it multiplicity 2. It could be 4, it could be 6, but they're asking for a polynomial of least possible degree. So we know it has to be an even multiplicity, and the smallest even number is 2. So -1, multiplicity 2, and then another 0 at 2. Let's go ahead and change those into factors. So we'll have x plus 1 and x plus 1 and x minus 2. So same idea as the last one. We've got f of x is equal to, we don't know what the stretch is, so let's keep it as a. And then x plus 1 times x plus 1 times x minus 2. If we multiply this out, this time I'm going to multiply the x plus 1's together because I know what that comes out to be. So x squared plus 2x plus 1, and that times x minus 2. And then multiply by x minus 2. And we'll get x cubed minus 3x minus 2. So if we look at that, it would have a y-intercept of -2. But our y-intercept is not at -2. In fact, I tried to make the graph pretty clear. Do you see how it is at -1/2 for the y-intercept? So the stretch we would have to incur, the number we'd have to multiply by to get -2 to become 1/2 is 1/4. Right? 1/4 times -2 is -1/2. So that would give us the correct y-intercept. So let's make a 1/4. And then we'll distribute through the 1/4 to get it into our standard form. And we'll have 1/4 x cubed minus 3/4 x minus 1/2, which matches the y-intercept there. So the graph of this function has the y-intercept at 0, -1/2, and it has the x-intercepts at -1 and 2, because by design, we made those happen up above.